In this problem, we have a box, like you see in the picture, sitting on an XYZ coordinate frame, and there's an electric field in the X direction. So this electric field is not constant, but it changes with X. So it only depends on X. It doesn't depend on Y or Z. Now there is some charge enclosed within this box, and it's equal to negative 24 nanocoulombs. We are also told that for the value x equals 0, the electric field strength E sub x is equal to 125 newtons per coulomb. Part A is asking what is the electric flux through surface 1 that is shown on the picture. Now, if you think about it, surface 1 corresponds to the point where x equals 0, right? That's the YZ plane, and that's exactly where x is equal to 0. Anywhere on the surface, x has a value equal to 0. So this is where electric field magnitude is equal to 125 newtons per coulomb. To calculate the flux through the surface, let's simply multiply the electric field strength, which is uniform on the surface, right, everywhere on the surface, times the area of the surface. And because this is outward from the volume, this is going to be a positive flux. So here's my formula. Flux through area surface 1 is equal to the electric field magnitude at x equals 0 times the surface area of surface 1, which I called A sub 1. And let's now substitute the values. The area in question is just a rectangular area of height 2 meters and width 3 meters. So that's 2 times 3, 6 meters squared. And we multiply that by the electric field magnitude through that surface, which is 125 newtons per coulomb. And the flux is equal to 750 Newton meter squared per coulomb. I have also added a superscript to this flux variable. I call it flux 1 because this is the one through surface 1. Now in part B, we are being asked to calculate the flux through surface 2. Now if you look at surface 2 is parallel to the x direction, right? And the electric field is also parallel to the x direction, so it's in the x direction. So then because the electric field itself is parallel to the surface number 2, there is no flux going through this surface. So the flux through surface 2 is equal to 0. Let me actually write that down. Flux, electric flux through surface 2 is equal to 0, like so. Part C is asking what is the magnitude and direction of the electric field at the opposite surface of surface 1. So that's the back surface of the box. For that, let's apply Gauss's law since we know the enclosed charge. According to Gauss's law, net flux throughout this volume is equal to the enclosed charge Q divided by epsilon 0. So what is that net flux? Well, there's flux through surface 1, there's flux through the back surface, and that's what we're looking for the electric field at that surface, right? And then there's flux through the other surfaces, the side surfaces, surface 2, the opposite side of that, and the top surface and the bottom surface. So the two surfaces on the sides and the top and the bottom, those are all parallel to the electric field. Those are all parallel to the x direction. So flux through those surfaces will be 0. So the only two surfaces through which there's a non-zero flux is the front surface, surface 1, and the back surface. So let's manipulate our equation, work out our equation to reflect that. So flux through the back surface plus flux through the front surface, that's surface 1, is equal to total charge enclosed within this box divided by epsilon 0. Now the electric flux through the back surface is simply equal to the electric field at the level of that surface, which is what I'm looking for, times the area, surface area of that back surface, which is again just a rectangular area with height 2 and width equal to 3 meters. Now let me rearrange this equation and isolate my unknown. E back, that's the electric field on the back surface. Here's what I get when I isolate my unknown. Let's go ahead and plug in the numbers and calculate the value for the electric field. And here's my result. So I get the electric field value negative 577 Newton per Coulomb. Now, does that mean the electric field is pointing in a negative x direction? Actually, in this case, it doesn't mean that. Now, when I plugged in the value for the or substituted the expression for flux through the back surface, I assumed that it was just E times A, right? Assuming the electric field was pointing away outward from that surface as well. So my initial assumption was that the electric field was pointing in a negative x direction. So that's the only way to have a flux pointing outward from that surface. But then I got the negative result here, meaning my original assumption for the electric field component was wrong, and the electric field in reality is pointing in the positive x direction on the back surface as well, and that means a flux into the back surface. So really this means 577 newtons per coulomb on the back surface pointed in the positive x direction. Now part D is asking, is this electric field, overall electric field that we have determined or the existing electric field in this problem, is it due to the enclosed charge only, or is it a combination of the enclosed charge and some external charges? And the answer is this electric field is due to the combination of the enclosed charge within the box plus some external charges that we don't see in the picture. And how do we know that? Well, if you think about it, the enclosed charge in the box is negative, right? And what we would expect from a negative enclosed charge, we would expect the electric field vector on any surface to point inward into the volume, right? But that is not the case for surface 1. For the front surface, we know that the electric field is pointing away from the surface. And that is only possible if there are external charges that are contributing to the electric field.